So today we begin with the discussion of linear first order and ODE, and we will discuss a special type of nonlinear ODE called Bernoulli equations. But basically, we will use the technique for the linear first order ODE to solve this special type of nonlinear differential equation. So first of all, we consider an ODE. Okay, a response order, of course, you can see from the equation, and but it is linear in y and in y. So you can see that the y prime appears as a linear term, and the y itself appears as a linear term. So this is why we call it as a linear ODE. Okay, so in many situations, okay, for example, in the physical systems or in an electrical circuit, the system can be represented by a block. All right, so it's a box, I named it as L. And that is an input of x, and we have an output y of x. And sometimes we have an initial condition, okay, for the system. And quite often, such a linear system can be written or can be described by such a differential equation. So r of x here, it's just like the input of the system. And the y of x, is just the output of x. Okay? And the function p of x is used to describe the internal linear system. Okay, so once we solve this ODE and a given initial condition, then we can have the output of the system for each input output. Okay. So this is just a system point of view to describe an ODE. I think in this semester, some of you, I think most of you, registered to electric circuit course. So you will see in many electric circuit, it is usually modeled as a linear system, and quite often it is modeled by a differential equation. Even though this differential equation may be in second order, not only the first order. And but in general, it can be described by such a block diagram. All right, so let's see some example. Okay, so consider this first order ODE. now we can put into a standard form by divide both sides with cosine x. So you can have, okay? Alright, so here you have a standard form. So the P of x is just equal to the tangent x. And the x times secant x is just our input out of x. Okay. You can see that. Okay, now if the input is 0, means we have the 0 input. Alright? Now the system will be determined by the initial condition. Because you have initial conditions, so the system will evolve by itself, right? It's still evolving, so you have output signal too, even though the input signal is 0. Okay? So in this case, so when all of x is equal to 0, for all x in a, so for example, in an interval of interval, okay. So this first order linear body becomes 2. Okay. Right, and we give such OD as is a name homogeneous linear first order. Okay. So whenever the input is 0, then we call this linear OD as homogeneous. Now, so when you look at the homogeneous linear first order ODE, you can see that we can solve it by separating variables. Right? So right? So we have 1 over y, 1 equal to a minus. Okay, so we first move the second term to the right hand side. Okay, and divide both sides by y. So you get it here. Okay, so now we are in a separable form. And so we have natural logarithm of 1 equal to minus. And probably you can add a constant called system. So now 1 equal to plus minus exponential function of okay. Okay, and so we can write it down as x. Okay. So see. It's an arbitrary constant. we define, because exponential functions usually positive, so when we put the minus you can get negative number or positive number. And by the way, if c equals 0, then the solution is 0. So when the solution is 0, it is automatically a solution, right? Satisfy this equation. So c can be any arbitrary constant, including the 0. So when I can say when c equals 0, we have the trivial solution. And it is a common phenomenon to have the trivial solution, 0, real functions in any homogeneous systems, including maybe some of you have taken linear algebra last semester to learn the homogeneous linear equations, right? And the real solution is always one of the solutions for any homogeneous linear system. And for homogeneous linear ODE, the trivial solution, the zero solution is always one of the solutions. So this is it. Are there any questions about to solve such a simple homogeneous first order linear ODE? Any questions? All right. So if the input is not 0, so in general we have an input of x. Okay. We have a so-called non-homogeneous. Okay. So we call it non-homogeneous. Okay, so in general, our x is not 0. In this case, we will introduce an integrating factor to solve it. Okay? So now, right, depending on x. Okay? So now, right. So consider. So we multiply f of x on the both side of this non-homogeneous equation. So we have 1 plus equals to now the reason why we put such an integrating factor f of x is because we want the left-hand side Okay, we want the left-hand side of the equation becomes to, okay, becomes to f of x, y prime. So we want to, the left-hand side becomes the derivative of the product of the integrating vector and the y of this. We want this to happen. We want. And we can see that, if this is happen, what is the sufficient and necessary condition? Okay, so now by the product rule of derivative, we know this is equal to f of x, y prime plus f prime, x into y, right? Now compare the left-hand side with this expression. Okay, now this is equal to this one if and only if, this product is equal to the derivative of f, right? This is the only way you can have. So if and only if, right? So if this is true, then the left-hand side of this equation becomes to the derivative of the product. This is no way to go. So any useful integrating factor ever should satisfy this equation. Okay, should satisfy this equation. Okay, so we first find an integrating factor which satisfies this equation. Okay, so fortunately we can solve it. Okay, again by what? By separating variable, right? So you can see we have one of right. So this differential equation can be written in this separable form. Any questions? Yeah. Don't hesitate to ask any questions. If you have any questions, just calm down, right? No second thought. Just ask. Because everything will be more efficient if you ask. Okay, so now we have again. This is the natural logarithm of x, and here you have v of x dx. Right, and of course that you can have C star. So we select. So of course there are many possible choices of both f, but we select f of x, which is just equal to the exponential function of. Okay, so just select that. Okay, you can put C here, right? You can put any C, but you just select one. So we select this one, and okay. So this is our equation. Okay, so we are successful to find an equating vector f of x. Okay, and this f of x depends on the p of x. So now, okay, so now we have, so we say take one, right? So we have, exponential. Okay, this is our f of x. times y prime is equal to here exponential function of x, e of x times r of x. Okay? So the derivative of this function is this function. So by the fundamental theorem of calculus, we know that y is equal to the integration okay. Right. So this is just a simple fact for the fundamental theorem. So you can have this one, and so y is equal to e to the minus oh, I'm sorry, I forgot to put C here. Okay. Plus C times okay. This term depends on the input. Okay, so it is called the response to the input. Okay. And the second term is the response to the initial condition. So the initial condition will determine the constancy. We have an arbitrary constant, C here. So we need the initial condition to determine it. Okay. Any questions? Yes, please.
How can we get the equation from the fundamental theorem?
You mean the last expression?
Top.
Oh, top now?
Yes.
Okay. This is from here. This is the derivative. You can think about the product in the parentheses. It's just a function of x, right? Okay. So the derivative of a function of x is equal to this function. So to recover this function, you just take the integration of this function. This is called the fundamental theorem of calculus.
Got it.
Sound okay? Okay. Other questions? All right, so let's take an example to illustrate the procedure. All right, so y plus tangent x y equal to sine 2x. Okay. And with a limit condition y is 0 to 1. So consider Alright, so we have an initial value problem. So we have the first order linear ODE plus an initial condition. Okay. Alright, so now, so we see P of x is equal to the tangent x. P of x is equal to tangent x. Okay. And R of x is equal to sine x. So maybe we can use the double angle theorem to know that the R of x is equal to 2 times sine x times cosine x. Okay. And now we need this integral, right? The integral of P of x. So this integral, so actually, if you forget how to integrate trigonometric functions, just look up the table and you can Google it. Okay. So this is actually equal to the natural logarithm of the absolute value of the secant function. Okay, so this indefinite integral is equal to the natural logarithm of the absolute value of the secant function. And so exponential function of P of x dx, okay, which appear quite often, is equal to exponential logarithm secant x. Okay. So actually this is a secant x. Right? And what is that? This is our integrating vector, right? So we find our integrating vector f of x right here. Okay. So very fortunately, the integrating vector we find is just the secant one. Okay, let me know if you have any questions from this example. So let's identify that f of this function, this is our okay. This is our integrating vector f of x. Okay, this is the procedure how we find out an integrating vector. Quite a standard procedure. Okay, and now, so we know So this is, we need to evaluate this integral. So this is our, okay, so f of x is the secant x, but all x is equal to 2 times sine x times cosine x. So after the multiplication, so we know that this is equal to 2 sine x and 0. And so this is equal to 2 cosine x minus, okay. Alright, so the final solution. The final solutions. So y of x, which is equal to okay. So we have 1 over f of x and times minus 2 cosine x, okay. Plus c divided by f of x, okay. And so this is c cosine x minus 2 cosine square x. Okay? Because f of x is the secant x, so the reciprocal of f of x is just the reciprocal of secant, and the reciprocal of secant is just the cosine function. Okay? So the cosine function here. Okay? So this is c times cosine x, and the cosine is, so we have cosine square. Which is a general solution of the ODE. Okay? To obtain the particular solution, we use the initial condition, y0 with 1 here. Sorry. So this implies 1 is equal to, so when you put 0 here, 0, okay, so you get c minus 2. Okay. Because cosine 0 is equal to 1. And so you determine c equal to 3. Okay. That's y, x is equal to 3 cosine x minus 2 cosine square x. So this is our particular solution. Any questions? Okay, so we like to reduce some nonlinear ODE to linear ODE by suitable transformation. Okay. the transformation method is in general very useful technique to solve many difficult ODE. We will consider Bernoulli equation. Bernoulli equations is equations like here. G of x and the a in general is a real number. Okay? So if a is not equal to 0, so when a is equal to 0 or 1, it is linear, of course. Okay, so if a is 0, if a is 0, then this is just g of x is just like r of x. But if a is equal to 1, you can combine this term with this term. Okay. So when a equals 0 or 1, then this Bernoulli equation is a linear ODE. Okay, so now we consider other cases. A not equal to 0 or 1. Okay, so we consider this case. So now we should use a proper transformation again. Okay, so we define u of a new function to be the 1 minus a's power of the y function. Okay, so this is the transformation we will use. So 1 minus a can be positive or negative. Okay, but because a is not equal to 0 or 1, so 1 minus a will not be equal to 0 or equal to 1. So you will see the condition for 1 minus a. Okay, so then u prime x, the derivative of u, okay, is 1 minus a. I change the one. Y of minus a, okay, and 1 prime, okay. So this is just by change the one. Any questions? Again, if you have any question, just raise your hand. Okay, now, so now y prime is equal to g y a, okay, minus p and y. Okay. So we just substitute y prime into here. Okay, so now we have two terms. These two terms cancel. So we have 1 minus a and g minus g minus p y minus a. So we just move these vectors into this expression. So we cancel it and combine this together here. right? Now, remember, the y minus s power of y is defined to be u. So this is equal to 1 minus a g u. Okay? Alright, so now we write it in standard form. Okay. Now we have a linear first order ODE. Okay. So we are successful to reduce a nonlinear first order ODE to a linear first order ODE by using this transformation. Okay. Any questions? And you know how to solve it, right? You know how to solve this linear first order ODE by integrating factor. Alright, so let's take an example. Consider the logistic equation. Y prime is equal to a y minus b y squared. Where a and b are constants. Alright? The logistic equation is a famous differential equations in engineering. Okay? So you can see that logistic equation is a special type of Bernoulli equation. The A is equal to 2. So now A equal to 2. So U by definition is equal to the 1 minus A. So it is just equal to the reciprocal of 1. Okay, so U is just defined to be the reciprocal of 1. And P of x is equal to minus A. Okay, and the G of x is equal to minus B. Right? Compare with the standard form here. So we have U prime plus 1 minus 2 minus A U equal to 1 minus 2 minus B. Okay, we just write down the linear ODE. Yeah. Okay. So this is equal to U prime plus AU equal to B. Okay. Very simple linear first order ODE. Okay, so you turn this logistics equation into this linear ODE through the transformation. Here. So you get here, right? And the procedure to solve this linear ODE is quite standard in already learned before. So we can write the solution immediately. So we have U equals to C minus 8x plus divided by n. Okay. Alright, so we can solve this linear ODE, right? Okay. And remember, U is equal to the reciprocal of Y. So this is equal to 1 over 1 here. So finally, the solution is equal to okay. All right, and note that for this solution, if we return to that, but because the transformation is the reciprocal one, so this is only true if y is not 0, right? If y is not 0. So I have to emphasize so we have to assume that the y from the solution y is not equal to 0 for all x in a certain open interval, right? So basically, when we do the transformation, we exclude the trivial solution. But here you can see, when y equal to 0, this OD is satisfied automatically, right? When y is 0, you can see that this equation is satisfied. So a solution. And this solution has been excluded from this transformation. Okay, so sometimes we have to be very careful when we do the transformations. Some possible solution has been excluded. It's been excluded. And you have to go back to the original ODE to see what kind of solution has been excluded in the following procedure. Okay? Even though this is the minor, but if you want to have a solution which is 100% correct, then this is something you have to consider carefully. Any questions? Any questions? So, the logistic equation Okay, so see here, y prime is equal to a function y. So the whole equation does not depend on the independent variable x explicitly. The dependence is implicitly in here in this derivative. Okay. So we call it as autonomous ODE. Okay, so autonomous ODE. Okay, and this equation has equilibrium solution, or we call equilibrium point. Okay. So the way is that we set f of y equal to 0. Okay, to find zeros, say yi, of the function f1. Okay, so we solve this function 0. When the value is 0, y prime is 0. So the derivative is 0. When the derivative is 0, it means that the instantaneous rate for change is 0. Okay. It means that we reach to an equilibrium situation. So for these zeros, y prime is 0. And the y x equal to yi are solutions. Okay. So you get constant solutions. It means that the solution is constant. It means that you have reached to the equilibrium point. So the output will not change anymore. Okay? Will not change anymore because the derivative are probably equal to 0. So you have. Okay. Sometimes we call these zeros critical points. So an example here. Y prime is equal to. Okay. So suppose y of y, f of y is a polynomial and can be factorized into y minus 1 and y minus 2. So y equal to 1, 2, or critical points. Okay. So that's y of x equal to 1, and y of x equal to 2, or equilibrium solution. Well, this situation can be illustrated by drawing the direction field that we learned in the second section. So, so you can see that. Okay. So this is y axis, this is the x axis. Okay, and we have y, point 1 is equal to 1, 2. So we have two critical points. And at these points, the direction field, because the slope is 0, so the segment is 0 here. But for here, and you get bigger in the future, it becomes and here you have the negative slope. Okay, so you have negative slope, right? And but in this region, you have positive slope again. Okay, this is direction field. So you have this is the direction field when you plot. Okay, and so you can see that the solution curve will approaching to this equilibrium solution, right? Approaching to that. So you can see that this is a stable one, stable equilibrium solution. But for this solution, it's unstable because it's going out, right? It's not easy to stay in this value, so it tends to going out. So this is an unstable equilibrium. So even though both are equilibrium solutions, but one is stable, the other is unstable. Okay? And the reason can be seen from drawing the direction field. Okay? So, okay, I'm sorry. We have to have 5 minutes break from now.